300 million tons is the exact weight of salt produced by the global industry each year. This volume is sufficient to blanket the entire Sahara Desert with a dense layer half a meter thick. One can visualize how the endless white crystals would cover the sand. But this is just the beginning. Why does humanity require such a colossal reserve? It seems like this is merely a kitchen spice. However, salt serves as the absolute chemical foundation of life itself. It maintains strict water balance and enables nerve transmission within the body. At first glance, these are simple grains, but in reality, they protect the cells of every living being. Machines harvest the resource from coastal flats and deep underground mines. The camera glides along the conveyor, where the raw material is refined and packaged. It transforms from a seasoning into a vital industrial ingredient. The process is only gaining momentum. The blue droplets of the ocean turn into white gold, ready for the next phase of the journey. 70 million tons of salt annually. Exactly this volume is generated by China, standing today as the world's leading producer. This figure accounts for nearly 1/3 of the total global output. For thousands of years, the mineral has coexisted with humanity, linking the deep sea with the land. Statistics show that about 30% of the world's supply is produced from the ocean, while 40% is extracted from vast underground mines. But this is just the beginning. How is it physically possible to extract millions of tons of pure crystals starting from just a single drop of seawater? The sheer scale of industrial evaporation seems impossible to track with the naked eye. It requires a fully mechanized system where automated harvesting and closed-loop refining work in unison to separate the mineral. From the expansive fields of Tianjin and Shandong to the coastal islands of Hainan, technology controls the process. One can notice how automated harvesters move through the pools, gathering the raw material layer by layer. It seems simple to collect the precipitate, but in reality, the cycle involves complex drying and purification stages to ensure quality. Meanwhile, nature preserves over 400 vibrant salt lakes across South America, Africa, and Oceania. It is visible how these natural crystal factories shimmer under the sun, attracting millions of visitors each year. Transition to the next level, attention returns to the origin point where the salt is born. 2 to 3 times faster is the speed at which evaporation occurs on specially prepared pond bottoms compared to natural soil. Every December, as the dry season begins, the coastal salt fields enter their critical preparation phase for a new production cycle. Salt workers start by renovating the entire pond system, dredging thick mud, leveling the surface, and reinforcing the dikes to securely retain seawater. The pond bottoms are either lined with dark cement or compacted with clay, which not only prevents seepage, but also enhances heat absorption from the sun. When the salt fields are finally ready, the workers manually crank open the heavy sluice gates, letting the first streams of seawater flow in. But this is just the beginning. Under the blazing sun and the salty winds from the open sea, the greenish waters pump through a network of shallow channels. The liquid wins its way into each pond, where every operation is precisely calculated. Why is the water kept in the settling ponds for 24 to 72 hours before moving forward? It would seem faster to move immediately to evaporation. This pause allows sand, silt, and natural algae to settle completely to the bottom, purifying the liquid for the next stage. Only when the tide reaches its highest point does the water reach a salinity of about 3 to 5%, the ideal level for later crystallization. The workers then use a refractometer to check the salinity before opening the valves to let the water continue into the concentration ponds. At first glance, the water sits stagnant under the sun, but in reality, a magical interplay of sunlight and wind is taking place. Under heat exceeding 30 degrees Celsius, each molecule of water slowly evaporates. leaving behind a solution that grows ever more concentrated. Each pond varies in depth, surface area, and evaporation time, arranged in sequence to gradually increase salinity from 5% to over 25%. One can notice the color of the water shifting from deep blue to milky white as a clear sign that crystallization is near. In modern salt farms, automatic sensors measure salinity and water levels by the hour, while in traditional ones, workers rely on keen observation. It gets more complex further on. Because a single moment determines everything in the journey from seawater to white crystals, the brine is directed into the crystallization ponds when it reaches a saturation level of about 26%. These shallow basins are only 3 to 5 centimeters deep, with flat, mirror-like surfaces lined with dark cement or tightly compacted clay to maximize heat absorption. Under the scorching sunlight, the pond floor can reach up to 50 degrees Celsius. It is visible how up to 8 millimeters of water evaporate each day, leaving behind the first delicate layers of salt crystals clinging to the bottom. At first, they appear as a thin film, gradually thickening and turning pure white like crystal as the process reaches its completion. After nearly 2 months of hard work, when the fields have dried and are covered with a shimmering layer of white crystals, the harvest season officially begins. Salt workers use bamboo rakes and aluminum shovels to gather the layers of white salt, pushing them gradually toward the edges. Every movement must be precise and steady to avoid scratching the pond floor, which could affect the next harvest. Once collected, the salt is piled into cone-shaped mounds over a meter high, left to drain naturally for 24 to 48 hours before being transported for refining. In countries like Vietnam, India, and Senegal, the image of salt workers wearing conical hats has become an enduring symbol. Transition to the next level. Meanwhile, in modern salt fields such as those in Tianjin, China, or Australia, harvesting is carried out by automatic salt harvesters. When sensors detect that the salt's moisture content has dropped below 4%, rotary rakes or suction conveyors begin operating, gathering the salt into long rows before loading it onto trucks or conveyor belts that transport it directly to the refining plant. Each machine can process between 30 and 50 tons of salt per hour, reducing the harvest time for an entire field spanning dozens of hectares to just a few hours. Seeing these massive mountains of salt, the question arises whether taking so much material from the sea makes the ocean any less salty. The production cycle simply concludes this phase, leaving the balance of nature undisturbed. "7 million tons of salt annually leave the depths of a single underground mine. The Goderic mine represents a vast subterranean labyrinth stretching for dozens of kilometers beneath the Canadian surface. This volume is sufficient to cover the entire North American highway system during the winter months. It preserves a mineral resource formed by ancient oceans more than 400 million years ago. But this is just the beginning of the extraction journey. Work shifts do not start with the sunrise, but with a 500-meter descent in a vertical elevator ride. One can notice how workers navigate through highway-sized tunnels in specialized transport trucks. They travel between vast salt chambers where the extraction actually takes place. The scale of these underground cities rivals surface infrastructure. Engineers operate continuous miners, massive machines exceeding 15 meters in length. It is visible how dozens of rotating steel teeth cut through the solid rock face with relentless force. These mechanical giants release hundreds of tons of salt every single hour, letting it fall to the mine floor. It gets more complex further on. Why are enormous pillars of salt deliberately left standing in the middle of the extraction zone? It would seem efficient to mine everything, but without these natural supports, the geological structure would collapse. This technique, known as the room and pillar method, guarantees stability while forming an intricate network of tunnels stretching for many kilometers. Large bucket loaders or conveyor belts collect the loose material and transfer it into underground haul trucks with a capacity of 30 to 40 tons. At first glance, the transport seems like a simple logic of movement, but in reality, environmental control is critical. A mist spray system suppresses airborne particles while the tunnel network is ventilated under pressure. The trucks deliver their load to the primary crusher station, located directly within the mine. Here, the massive blocks are crushed into smaller uniform pieces measuring 20 to 50 millimeters for easier transport. One can observe the crushed salt rising to the surface via a skip hoist or an inclined conveyor belt. The automated system operates continuously to ensure a steady flow of raw material to the top. Everything only gets more complicated at the surface. The material accumulates in enormous dome-shaped storage facilities, awaiting distribution. From here, the salt is shipped for road de-icing, chemical production, or food processing industries. Some batches head to refining plants for further purification. The mineral extracted from the dark depths is now ready for its industrial application. 20,000 tons of cargo capacity allow a single heavy-duty ship to transport the mineral harvest across oceans to destinations worldwide. The journey of salt, whether extracted from the depths of the earth or harvested from the sea, transitions here into a stage of massive industrial logistics. In coastal regions, front loaders and mobile conveyors ceaselessly transfer dried heaps onto trucks or barges. One can notice how the white convoys of trucks driving along coastal roads in China, India, and Vietnam have become a visual symbol of the harvest season. Why is the transportation process different for inland sources? It would seem that surface transport is sufficient for all extraction methods. But in underground mines like Goddard in Canada or Winsford in the United Kingdom, the logistics require vertical integration where cranes with clamshell buckets and automated conveyors load the raw material directly onto cargo vessels. These shipments travel from chemical factories in Europe to the snow-covered highways of North America. However, this is just the beginning of the transformation. Inside modern refining plants, the raw crystals must undergo a fully enclosed cleaning process to achieve purity. Feed hoppers pour the raw salt onto vibrating conveyors, where the separation of soil, sand, and metal particles takes place using electromagnetic separators and multi-layer mechanical sieves. Why is the salt washed with a saturated brine solution instead of pure water? At first glance, adding more liquid to the crystals seems counterintuitive during a cleaning phase. This specific technique is used because the difference in density allows impurities to be washed away without dissolving the salt crystals, which would disappear in fresh water. The mixture is then sent to centrifuges to remove excess fluid. Rotary dryers heat the material with air ranging from 120 to 150 degrees Celsius. The moisture content drops to below 0.5%, ensuring the grains become crisp and free-flowing. It is visible how the crushers split the dried mass into specific grain sizes for different industries. Coarse salt goes to industrial sectors, fine salt enters the food market, and ultrafine particles serve medical needs. But the process is only gaining momentum. Precision mist spraying systems enrich the product with iodine or trace minerals to meet international standards. At first glance, the factory environment appears sterile and controlled, but in reality, salt remains a silent enemy that corrodes metal equipment, including stainless steel, faster than almost any other substance. Therefore, maintenance is a constant battle alongside production. Once the desired purity is reached, the material moves to the automatic packaging phase. Screw conveyors transport the salt from intermediate storage silos into dosing hoppers equipped with electronic weight sensors. Vertical form-fill seal machines, which are the standard in factories worldwide, pack 60 to 100 bags every minute. Weights range from 250 grams to 50 kilograms depending on the production scale. The packaging material consists of multi-layer polypropylene film, which is moisture-resistant and pre-printed with QR codes for traceability. One can notice how automated arms group small bags into bundles of 10 or 20 packs, while larger sacks are stacked on wooden pallets. The entire cycle in large-scale factories in Egypt or India takes less than 2 minutes thanks to PLC control systems. And this is not the limit of salt's transformation. In the realm of traditional Asian medicine, a special variety known as bamboo salt is created through a meticulous craft. Artisans pack unrefined sea salt into mature bamboo tubes that have aged for 3 to 5 years. Engineers of this traditional method seal the ends with yellow or red clay to prevent leakage. The tubes are fired in kilns at temperatures ranging from 800 to 1,500 degrees Celsius. The firing process can be repeated up to 9 times. During the final firing, the salt melts into a solid mass and takes on a distinctive dark purple hue. After cooling naturally, the rock-like substance is broken and crushed into powder. This marks the end of the long production chain, leaving the salt ready for its final application.